Welcome. We are doing Equilibrium Lab, and so would initially, if you were here with me, we would have you make the solutions that we would be using today. And so there are 4 solutions that we need: silver nitrate, sodium carbonate, copper sulfate, and cobalt chloride. So you would make those solutions. And so what I need you to do for me is pick one of those 4 solutions, whichever one you want, and do the calculation for it, so you can figure out how many grams you would need to weigh out to make a 50 milliliter solution for the first 3, silver nitrate, sodium carbonate, and copper sulfate, a 0.1 molar solution, and in the cobalt chloride situation, you'd need to have a 1 molar solution. And so what I am going to do now is do the first experiment, which is section B, and this is 1 milliliter of silver nitrate, and here I want to put 1 milliliter of sodium carbonate so you can see what happens when we mix those together. So to do this, I need to put in 20 drops. 1, 2, 3, 6, 7, 8, 9, 10. 20 drops of the sodium carbonate. All right, so as you can tell, these lovelies are both clear solutions. And we're going to mix them together, and hopefully something's going to happen. And indeed, we see a precipitate. Hold that still so you can look at it. Okay, so it now becomes incumbent upon us to use our knowledge of the solubility rules to figure out what is that precipitate. So I'm going to not talk for a minute and let you figure that out, and then come back and talk some more. Okay, so hopefully you figured out that we do have a precipitate here, and it's starting to settle out a little bit. And so we're going to give this a little bit more time to settle out. So we're going to go ahead and stop for a moment and then come back when this is set. Okay, we've let it sit for a moment, so let's have a look at it and see what's going on. Hopefully you can see the distinct band of solid there at the bottom. And the next thing that we're supposed to do is we're supposed to add some more silver and figure out what happens if we add more silver. So I got my bottle of silver nitrate here. Go ahead and get me a little bit of that. I'm going to go ahead and add some more. Let's see if we can see something happen. Do you see more precipitate for me? Okay, so we have more precipitate forming. Now, this brings up the age-old question, right? If you're not part of the solution, what are you? Right? There's that age-old adage that if you're not part of the, if you're part of the problem, if you're not part of the solution, then you're part of the problem. Well, in chemistry terms, if you're not part of the solution, you're part of the precipitate. So that's what we have here. Have we identified what the precipitate is yet? Hopefully we can use our solubility rules to find out. Okay, I don't want to give that away because that's an important part of all of this. I will say one thing. One of the compounds in the precipitate is carbonate. Hopefully we can figure that out. Now, the next thing that we want to do is we want to add acid. And if we add acid to a carbonate, everyone should know that that should make bubbles. We're going to make carbonic acid and water. So what I have here is a 6 molar bottle of nitric acid, excuse me. I'm going to go ahead and add some of that nitric acid to my solution here with the carbonate. So I put some of that in there. Oh my, some things are happening there. Okay, so it cleared up. Still have some precipitate at the bottom. I think we need to still add this until all the solid dissolves. We're starting to see it dissolve there. So we got some bubbles. Looks like we got rid of all the solid. It's all gone. Okay, so we've added enough nitric acid to make that happen. Now, what reacted with the nitric acid? Was it everything in the solution, or was it just the parts of the solid? That is an excellent question. We know for sure carbonate did because we had bubbles made. And what was connected to the carbonate? Hopefully you figured that out. And so when you write out your equation for that second part, because we've already written out an equation for the formation of the solid, what reacts with the acid is not everything that's in solution, because some of it is already ionized and floating free in solution. Some of it is in a solid, and so what happened was the solid went away, so that meant the compounds in the solid are what reacted with it. So the carbonate piece and whatever was attached to that carbonate was the starting material when we added the acid, and then when we get done with that, we should end up with water, carbon dioxide, and then the ions that would come out of that solid. Okay, so it was solid, whatever the thing is paired with carbonate, reacting it with the acid, and then we get water, carbon dioxide, and the ion that's left over from that. So there should be some nitrate and whatever that other piece is. All right, so that's experiment B. Go ahead and write up your equations and figure out how that goes together. We're going to set up for the next reaction, which is copper. Okay, so we're looking at copper and ammonia as we look into this. So we want to go ahead and make a compound. So we want to start off with 2 milliliters of our copper solution. So we'll go ahead and get that going and get ourselves 2 milliliters of our copper solution. So right here. Okay, so there's 2 milliliters of our lovely copper sulfate, looking nice there. It's hard to see it in the background there, but it's a nice blue. And to that, we want to add our ammonia. And we're going to add 4 milliliters of this. And hopefully it's going to do some fun stuff for us. So here we go. Okay, so we can see the colors that are forming there. The total volume is 4 milliliters. So there we go. Oh, we're starting to get some differentiation there. Starting to be a solid forming there at the bottom. And then we have this dark blue liquid there. So let's go ahead and mix this around. And then we'll let it sit for just a minute and we'll come back to it. Okay, so we've let this solution sit for a minute. We can see the 2 layers, hopefully. There is a solid at the bottom that's a little bit white. Okay, let's see if we can do it that way. There should be just a little bit of solid there at the bottom. We can see that's the whiter part, and then above that we have the dark blue. So based on what we know from the equations that are in our lab, which should be the dark blue part? Is it the thing that's the solid, or is it the thing that is still aqueous? Right, and then, so on the bottom we have the solid, and in this we have the aqueous part, and they both are products of the addition of the ammonia. And the ammonia is going to make it basic, so it's going to make hydroxides, and the individual ammonias are going to interact with the copper to give us that nice dark blue color here. So the next thing that we want to do is figure out what would happen if we add acid to this, because it's going to make it go back the other way. We're going to have the equilibrium shift when we add a stress to it. So we have this, and we should be able to figure out the equations of what's going to happen. So if we add acid to a hydroxide, it should go to water. And if we add acid to a ammonia, it should go to ammonium. It should make that. So we're going to go ahead and take a little bit of hydrochloric acid. We're going to add it to the ammonia. It should cause the equilibrium to shift on us just a little bit. So let's go ahead and mix that together. Might need to add a little bit more of the hydrochloric acid. Go ahead and add some more acid to it. And you should start seeing that dark blue and the precipitate start to go away. So a little bit more acid. You should be able to see the precipitate layer just a little bit better. We're going to add some more acid here. See if we can make it go back to its initial coloration. And there we go. Back to that nice light blue. And we're dissolving some of that solid down there. That's what's going on at the bottom there. So we want to get all of that dissolved. And while that's dissolving, we need to ask ourselves what happened. So what's going on? We're shifting the equilibrium back and forth, and the equilibrium that we're having is the copper making the compound of copper hydroxide and copper ammonia complex. And as we add the acid, it's reacting with the ammonia to make ammonium, the hydroxide to make water. And so as it becomes more acidic, we lose those compounds. So how do we make those compounds come back? What in the equilibrium should we add to make those compounds come back? Well, how did we get them in the first place? We added ammonia. So let's go ahead and add some ammonia and see if we can get those back. Look at that. Get the color back. Okay. And so if we let this sit long enough, we would end up back with more precipitate, and it'd all end up. Okay, so we did that. We shifted the equilibrium, and we made the ammonia complex with copper, and all set together. Okay, so now we need to get rid of our copper solution, move on to the next portion. Okay, the next lab experiment we want to do is use the ammonium ion and figure out its equilibrium. So we're going to go ahead and try and dissolve ammonium into this 2 milliliters of water. So here is my jar of ammonium chloride, and I'm going to go ahead and get myself a sizable scoop just to make sure. Maybe I might need to put this down so I can really get myself a scoop. There we go. Give me a scoop of the ammonium chloride and try to dissolve that as best I can. What I'm hoping to make here is a saturated solution. So I'm going to go ahead and agitate this the best that I can to try and dissolve my ammonium chloride. I want to have all of the solid dissolving it as best I can. Now I'm feeling this because I know that there's a temperature change involved in this one, and this is getting cold. So this should tell us that the solution process, right, that we should be familiar with is causing it to be endothermic. So that means that the energy it takes to disrupt the water and the ammonium chloride, that energy is more than we get from mixing ammonium chloride with the water. Okay, so we want to go ahead and mix this together as best that we can. Now, in this specific situation, because we're making a solution, this is not a chemical reaction as we know it. It's just a solution process. And so the solid is going into solution, right? And so we're taking a solid ammonium chloride and we're turning it into aqueous ammonium chloride. That's the procedure that's taking place. So when we write out the equation, we want to make sure that that's what is represented on the page. So I'm just trying to make sure that I get as much of the solid there as I can. Okay, and so it's good that there's a little bit of solid there at the bottom, and there's some solid in the liquid as well. So I'm probably gonna have to let this sit. But what we wanna make sure is that there is as much ammonium chloride inside of this test tube as inside of the liquid of the water as possible, because for this next part, the equilibrium, we need it to be a saturated solution. So we're gonna go ahead and pause for a little bit. You won't notice it, but I'm just letting you know, and then we'll come back when this has all been dissolved. Okay, we've let it sit and we've stirred it and we've made sure that we have a saturated solution of this. So we're gonna go ahead and pour off all the liquid from the top of this and put it in a different test tube. So the supernatant is the liquid above the solid, and so we're gonna go ahead and pour all of that into here so that we have just a liquid Okay, and so we have the liquid there, and then we're going to add some hydrochloric acid to it and see if we can make it shift back. So we're going to go ahead, 1, 2, 3, 4, 5, 6, 7. I don't know if you can see, but we are making little crystals. That may be hard to see in all of that. There is some solid starting to form inside of that. So we're shifting the equilibrium back towards the solid. So we're getting some solid precipitation coming out. And so we have shifted from the solution to the solid. So we're getting precipitate. And so that's what should happen in all of that. That one, it's better to witness in person. So not much I can do about that one, but there it is. We've got one more experiment to go here. And so we'll get set up for that one. All right, so we have our last experiment here, and we are looking at putting some cobalt, this is the 1 molar cobalt solution, into a test tube and trying to identify what happens. So this cobalt right here is in a aqueous solution, so it's surrounded by water. So there's about 1 milliliter of it. And so this is surrounded by water, and so it's important that we start off with the realization that it has been hydrated. And so all of the cobalt ions are not in contact with chloride ions. They're surrounded with water molecules. And so in your lab, there's a way to write out the formula with it with a bracket around the water. So waters are surrounding the cobalt ion. But to get the waters away from the cobalt ion, we need to flood this solution with a bunch of chloride ions. And the way that we can do that is with concentrated hydrochloric acid. So we're going to go ahead and put a couple of drops of that in here so you can see what happens when we add concentrated hydrochloric. There's 3 drops, 4 drops, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We'll go ahead and give that a... Okay, so with 15 drops of hydrochloric acid, it has that purple color to it. So we're making a different compound, and we're surrounding all of the cobalts with chlorine. So let's just give it a couple more drops. There's 16, 17, 18, 19, 20. Okay, so now it's starting to turn deeper purple. Okay, so there is an equilibrium that's going on there, and we're surrounding the cobalt now with chloride and not water. And so that's the different compound that we see, and that's the color that we get from it. So we're taking the water that's hydrated and now surrounding it with chlorine, and it is giving us that color. So now we need to investigate that equilibrium. So let's go ahead and put our dropper down and see if we can find some things to help us find the equilibrium. So I'm going to look around real quick and come right back. All right, in order to shift the equilibrium, we need to subsequently surround our cobalt with water and chlorine. So we're going to add some more water and see if that shifts it back to that red color. So I'm going to add some more water, and lo and behold, that purple color is less and less, and now we're back towards that original red. I'm going to add just a little bit more. Okay, and so I'm back to the red. I want to surround it with chlorine again, so I'm going to add the hydrochloric acid, and if I add more to it, I do see that blue color emerge again. Okay, and then just one more time, just to make sure that we're doing it right, more water means red. Okay, so we're getting that all together, and we'll just go ahead and mix that up real quick so we can have it all be red. Okay, and so if I wanted to turn it blue again, I would just add more hydrochloric acid, and that's the equilibrium back and forth, back and forth. So we surround it with water molecules, it turns red. We surround it with chloride ions, it turns blue. Now, we want to see what the temperature effect is for this. We need to devise our own reaction. So what we're going to do is we're going to take 3 different setups, and we're going to set them up with the exact same concentrations of everything. So it was about 15 drops of hydrochloric acid. So let's go ahead and put our 1 milliliter of cobalt chloride in 3 separate test tubes, and then we're going to put them at different temperatures. So one at cold, one room temperature, and one hot, and see if we can determine whether or not this process is endothermic or exothermic. So I'm going to set that up and I'll come right back. Okay, so here we have 3 test tubes with the various colors, and we're going to set them into different situations. So here we're going to leave the room temperature one. Here we're going to take our ice bath, and then over here I'm going to go grab water that's been sitting on a burner, and it's above 50 degrees, and so I'll just go grab that real quick and turn this off. So this water right here has been on a hot plate, and it is very warm. So we're going to go ahead and set those all right there. And so this is our room temperature one, this is our heated one, and this is our cold one. You can see, I'm going to let those sit for just a minute, but you could hopefully see, let me back this up so you can see it, that we're starting to see a color change in the cold one. The warm one is still a very dark blue, and this is this color. So these are both purplish, and this one's turning into a lighter purple as we let it sit. Okay, so that might tell us what's going on. We're going to let this sit for a little while and come back. Okay, we've let this sit for about a minute, and if we look at these are pretty much the same color. Although this was a deeper blue, and this one is a lighter purple than the rest. Now, what I want to do now is add a little bit of water to each of these, and then put the same amount and see if that makes a difference. Because we know that if we add water, it makes it go back towards the red. So I'm going to add 5 drops. 1, 2, 3, 4, 5. Mix that up, and I'm going to put that in the cold. Okay, I'm going to put 5 drops into this one. 1, 2, 3, 4, 5. Okay, mix that up, and then I'm going to put 5 drops into the warm one and see what happens. 1, 2, 3, 4, 5. Okay, put it back in the hot. So after adding 5 drops, we've lessened the severity of the chlorine around each of those. And so if we just take a look at the colorations of those, we can see in the cold, we're back to almost the original color, even though we have chloride ion in there. Here, we're kind of halfway through that purple. And even with the 5 drops of water, the hot is still that deep blue. So here's our 3 different colors. Here's cold, room temperature, and hot. So hopefully we can figure out whether or not this reaction is endothermic or exothermic. It looks like when we add heat, it pushes it towards the products, and when we add cold, it pushes it towards the reactants. So hopefully you can figure out whether or not that is endothermic or exothermic, and that completes this lab. So, all right.